Now we're going to look a bit more into the mathematical theory. So there's a class of ordinary differential equations which yield readily to deep analysis. So what I mean by that is mathematically they're very well understood. The form of these equations are, I can write it in a number of ways. So a fancy way is kind of saying, oh, it's some finite sum of constants which can actually be functions themselves, but here there's constants times derivatives equal to another function. Now that's obviously a bit scary looking, I appreciate. If we're being a bit nicer, we'll write, so it's some constant times some big derivative, which for us will pretty much always be the second derivative, plus more constants, then you get down to say a1 times the first derivative plus a0 times the function you're looking for equal to some 5t, which is another function. So we call this the differential equation homogeneous when the thing here is 0, which is going to be usually the case. In Maths 7009, we looked at 3 related ordinary differential equations that were actually of this form. So let us look at ei times the fourth derivative of x equal to minus w of x. So you've got the big constant here is ei, and then all the other constants are 0, and the 5x here is the minus w of x. So that's of that form. The other one was the second derivative of, we'll write the constants underneath just to show you, was this one. And then the fourth one was ei times the second derivative is equal to the bending moment. So the thing on the right hand side every time is the phi, and we'll just write down the things here. So this is like a4 is equal to ei, and then the other terms are all 0. So it is actually of this form. This one, the a2, the multiple of the second derivative is 1, and then a1 and a0 are both equal to 0. And this one, similar story, except the a2 is equal to ei. So what that means is that the differential equations we studied last semester, the beam equations, are very well understood mathematically. Now the killing thing is that, now I don't think, I said smooth here, I don't know how, does it have to be smooth, but the functions which we looked at last semester, which were like the loads, they're not smooth functions. So the delta functions and the u functions and the square brackets are not smooth. So actually they're very well understood up to a point. Okay, now we're just going to look at one particular one. Now I could write like ABC. I will write that for the time being. So we're going to look at a times the first derivative. You know what, I better just do it properly, just explain what I'm doing. So if you look back at the damped harmonic oscillator, it goes second derivative, first derivative function, okay, and so the first constant is the mass times the second derivative, which is the acceleration, plus another constant, which is the damping coefficient. Basically what I'm saying is, like, we've got this big general theory, but we're actually just going to look at one particular thing. So this is x dx dt, the first derivative, plus k times x of t. Now if I put it equal to 0, that's homogeneous. If I have an external force, so a force external to the damped harmonic oscillator, so for the door closer, that might be someone pushing and pulling the door. So the heavy analysis that we're going to look at basically says, if you've got a first order linear differential equation, which would be like a times dy dt plus b y of t equal to 0. This has only one solution, right? Don't worry exactly what that one solution is about, because you only anti-differentiate once. Now it's a bit more complicated. I mean, to actually solve this is a little bit messy. You would have touched on it very briefly in first year, but basically no. There's ways of solving this that wouldn't look totally mad to you. But basically what happens at some stage, there is an integration. At some stage, and this is the thinking that we're going with, you need to go from the derivative to the function. And if at some stage there is one of these antiderivatives, it's going to come with a plus c. So when you solve this equation for y of t, and this should be a t as well, you're going to have a plus c knocking around. So your solution is going to be in terms of t and this big C. And the big theory turns out that the c can be multiplied rather than added. Now I'll just explain how that might possibly happen. It basically turns out that if you solve this thing for y of t, you end up with the solution being something like e to the c plus roughly t. And this, so the big C you get when you do anti-differentiation ends up with an exponential. That's because if you solve this, you'd end up dividing by a y, you end up with a log of y, and to get rid of the log, you do the anti-log, which is the exponential, you end up here. And then you know stuff about exponentials. This is the same as e to the c times e to the t. And then if c is some constant, so is e to the c. So this is what we call the c. So that's how the constant, which is a plus c, ends up being multiplying. That's the first thing. Now, to find out what that constant is, you need an initial condition, some information about the relationship between t and y. Now, if you have a second order, you have two integrations, so there's two constants, c1 and c2, and you can show, with a bit of work, that's the heavy analysis that we're not going to look at, is that the two solutions, basically how you get all solutions is you get two solutions, add them together, multiplied by constants and add them together. So we're saying that the constants end up multiplying. The constants end up multiplying. The linear independence here is a fancy word that says you need two. So linear, it's a technical term, mathematical term. For us, it just means different. So one of these things essentially has, so the first orders has essentially one solution. It's going to be of the form e to the rt. This thing has two. So you're going to have like e to the r1t and e to the r2t. Now, if you ask, where the hell are you getting this e to the r? Don't worry about that yet. So the maths theory says, say the ones we're looking at, there's two different solutions. And so two essentially different solutions. You multiply them both by constants, you get more solutions. You add them together, you get more solutions. So essentially, all you have to do is find two different solutions. And you have all of them. See, the idea with that would be like, what would that be similar to? It'd be similar to if you had a 50,000 seater stadium and you knew that 49,998 tickets were sold. You know that there's two empty seats. And when you find the two empty seats, you don't have to keep checking. You know you have all of them. That would be the analogy. So it turned out that someone realized that for these types of equations written up the top, that exponentials are very likely to be good solutions. And that's because when you differentiate an exponential, you end up with multiples of exponentials. So what you're doing here, so imagine putting into this equation up the top some exponential. So all those derivatives are multiples of exponentials, and maybe you can find the exponentials that, so you're adding up all these exponentials that somehow they all kind of cancel each other out or something like that. Okay, so it turns, okay, now the thing is, if you got e to the rt, what's the derivative of e to the rt? Now if you go into your tables, you will learn that the derivative of e to the rt is r times e to the rt. Well, it'll say the derivative of e to the ax is a times e to the ax. So here, obviously, we're just doing it with r's and t's instead. And if you differentiate again, the second derivative, differentiate the first one. So fix the r. I'm differentiating now the first derivative. So fix the r, it's a constant, and now differentiate e to the r again. Well, you're going to get another r e to the rt. So the second derivative is r squared e to the rt. So because exponentials, when you differentiate them, you get multiples of exponentials. And because these things only have two solutions, if you just chance your arm with an exponential, it might work. And if you get two different solutions, you're done. So this is the idea of an ansatz. Yeah. Now we won't go through the full ansatz at the end. We're going to get to an easier place. We're going to kind of skip the theory, but I want you to understand this theory that you think you just have to find two solutions, so you just chance your arm. So here's that word ansatz. So we have our thing. So we're looking at a times second derivative. And I assume you're comfortable with y dashed of t is the same as dy dt. There's just different notations. Plus b times dy dt plus c times y of t equal to 0. So we're going to chance our arm with e to the rt. Now what was the second derivative? We showed at the end of the previous page that the second derivative of e to the rt was r squared e to the rt. Okay, plus b. So we're chancing our arm here. We're trying to get this working. So what we're going to do now is substitute the derivative of e to the rt in here. We get r times e to the rt. Plus finally c times e to the rt. And now we're really chancing our arm. So I don't know if I used this thing with you before with the exclamation mark. Try and force it to equal 0. It might be even more accurate because we really don't know what we're doing here. Question mark. Can we force a sum of exponentials to equal 0? Now what you can do is you can take out a common factor of e to the rt out of this. And what are you left with? A times r squared plus b times r plus c. Now one thing we didn't quite say, the coefficients, this ABC, they are constants. So there's some, like they could be 1, 2, 4, for example. Now, how can you force this to equal 0? We're still trying to force this to equal 0. Now the exponential is always positive, so it can't be 0. And the only way you have two things multiplied together giving you 0 is if they're both 0. Or sorry, if one of them is 0. E to the rt is never 0. So if you want e to the rt to be a solution, you need r to satisfy this equation. And this is called the auxiliary equation. And what you're going to be doing is, rather than going through that analysis, you're going to take the second order differential equation. It'd be nice if you knew in the background there's this idea of an ansatz. And you're going to go straight from there to here. And you're going to solve this equation. And you're going to know that the solutions of this, say for example, if you got r equal to -2 and -1, that e to the -2t and e to the -1t are both going to be solutions. So you would end up, let's write down our solutions. We know e to the -2t is a solution. We know e to the -t is a solution. And then I told you the theory that says that you can multiply these by constants. Now we won't call the constants C1 and C2, we'll call them A and B. And the theory also says you can add them together, and that gives you all of the solutions of the differential equation. Now it's heavier maths than I think you've ever seen. So you got this linear differential equation. The solution is a function, so it's some kind of a curve. You probably need the initial conditions. So that's the value of y at the start and the value of dy dt at the start. So you take this differential equation, this yoke, you form the auxiliary equation, Now the a, b, and c are specific numbers. You find the roots of the auxiliary equation, say -2 and -1, and then e to the root t are solutions. So you get e to the -2t and e to the -1t. And then the theory says if you multiply them by constants, you get more solutions. And if you add them together, you get more solutions. The idea is that, like, say the e to the -2t, that works. Put in the a, the big A. Now, the big A is a constant, so when you differentiate, nothing's going to happen. So you can take out the big A as a constant, and the rest of it is still going to be equal to 0. And you can also show if you add them together, essentially what you get is 2 bits added together, both of which are 0, which gives you 0. Okay, now there's 3 things that can happen that depend on the nature of the roots. Okay, which we'll probably start talking about today. Okay, so you're given okay, now we need to talk about complex numbers, okay? Because complex numbers come in. Now, it's not that, don't be too afraid, it's only going to be a tiny bit. So given, well, there's going to be a fun bit on the next page. Given a quadratic equation with a, b, and c real numbers with a definitely non-zero, you think that the solutions have to be real numbers. But it's not the case. For example, x squared plus 1 equal to 0. Is there any real number that satisfies that? Well, if there is a real number that satisfies it, x squared is equal to -1, and no real number squared is negative. So what we do in maths is we define a number I to be a solution of this. Okay? And then you can show that all quadratic equations, all these things, can be solved using complex numbers. And now most, usually you'll have like the real numbers, but the real numbers are like -2 is equal to -2 plus 0, is a complex number. So if you want to get solutions of this quadratic, you can find them if you use complex numbers. Okay, and the complex numbers are of the form a real number plus I times another real number. And I is the property that I squared is -1. Now, there's another thing. You've got I and -I, and essentially they're the same thing. Okay, so one of the things that you might see written down, which is kind of wrong actually, is to say that I is the square root of -1. That's very dodgy, right? Because the square root of a number is the positive square root, and I isn't positive. Because when you square a positive thing, you should get positive. So this is really kind of dodgy. It's far more accurate to say I squared is equal to -1. Now I say to you, well, what? You might be confused there. Well, I would say, well, what about -I? Why isn't that the square root of -1? Because -I by -I will be plus I squared is -1. So -1 has 2 roots, second roots, but you shouldn't talk of the square root because there's no real difference between I and -I. -I isn't negative. I is neither positive nor negative. It doesn't fall into that thing. Okay, so for the purpose, now that's possibly complicating things. For the purposes of Math 7021, all you need is this bit. That if you end up with the square root of -3, you may replace it with I root x. Now, strictly speaking, it should be plus or minus I root x, but don't worry about it, okay? So if you use, because, oh yeah, where's the plus or minus? Well, it's going to come from the -b formula. So you're never going to see square root of -3 on its own. It'll always be plus or minus the square root of -3. So you use the -b form, you get -3 in the square root. So you say square root of -3 is I times √3, and you get complex roots. Now, just to show that these are the same thing, we square the square root of -3, you get -3. And if you square the I √3, you end up in a roundabout way of -3 as well. So these are the same thing. Okay. So that's just a little note. So all the discussion below concerns a second order different. Now I don't know how far we're going to go here. So you have a times second derivative plus b times first derivative plus c times what you're looking for. You go straight to the auxiliary equation. Now you find the roots. Now what I'll be recommending is you factorize and then solve that equal to 0. But theoretically what you're doing is you're at the end of the day, you're going to get the same as the minus b formula. Okay. If the b squared minus 4ac is positive, this thing is a square root of a positive number, so you have two different roots, which we might call alpha and beta here. The plus one, so we could call this r plus, and we could call this r minus. That's two different roots. And if you have different roots, remember we were saying we needed different solutions, linearly independent solutions. So different roots, you automatically get different solutions, no problem. If the b squared minus 4ac is 0, you end up with a repeated root, and that causes a problem. So remember, if you get a root, so if you get a root of this, e to the rt is a solution. And we're saying that the solution space of this is essentially two-dimensional. You need two different solutions. Well, what if you solve the auxiliary equation for the e to get towards the e to the rt, and you get the same root twice? Well, then you're not getting a two-dimensional solution. You're in a bit of pain. And I think, yeah, well, okay. So that's the second situation. So the first situation is you get two real roots. Second is you've real repeated roots. And then the third situation is you've complex roots. And what will happen with the complex roots is there'll be the plus or minus, and you'll end up with this situation. This is probably easier to see if you actually solve one. Now we'll just show what happens with the different quadratic graphs. So the first case is when you have two real roots. So say r minus and r plus. The second, that's two real roots. That's the first scenario. The second scenario is you have one root. I nearly drew that really well. I want to just go and kiss it. Oh, almighty. So this is the repeated one, or repeated. So the red one is distinct. That's one particular behavior. The orange is you get the same root twice. That's a problem. And then we're going to have some crack with the complex one. So the complex one, where it's equal to 0. So maybe we'll just peel back a second. So what we're plotting here is not y actually, but ax squared, or even ar squared plus br plus c. So this one, and we're interested in where this is equal to 0. So this is the y coordinate. So the y coordinate is equal to 0 along the x-axis. So the red curve there cuts the x-axis twice. So the y is equal to 0 twice for real numbers r minus and r plus. The orange curve cuts the axis once, which means there's only one real number or it's equal to 0. Now, if you were to think about, and you can have a pause and think, what will happen with the complex roots? Where will the curve go? It can't cut it twice. It can't cut it once. It has to cut it not at all. So this is what the graph looks like for complex roots. And we're going to, okay, so we're going to have trouble with the repeated root to make, we need two different ones. So the red one is easy. The orange one is hard. The green one is good in the sense that you get two different roots, but you're going to be in a world of pain figuring out what this means. Well, I think it's cool. And that's what we'll start doing next week.